Hi, everyone. This is Grace Saba. We're going to just wait a few more minutes to give people a chance to log in. So in just a few minutes, we'll get started. Thank you. Okay, everyone, we're going to go ahead and get started. Thanks for attending today. I'm Grace Saba. I'm an assistant professor at Rutgers University and co-coordinator for MACAN. MACAN's other co-coordinator, Katie Goldsmith, who's the program manager at Mid-Atlantic Regional Council on the Ocean, or MARCO. She'll be presenting today on the work underway by the MACAN Monitoring Plan Work Group. But before I get into that, this webinar today is the fourth and final webinar in our second series. Previous webinars can be found posted on the MACAN website, and the website address is right there. Hopefully you have visited the site already before. And as this is our last webinar in the series, please send us ideas or requests for future webinars. And so today, Katie will be presenting on the efforts to date of the MACAN Monitoring Plan Work Group. Katie Goldsmith is the program manager at MARCO. It's a regional ocean partnership among the 5 Mid-Atlantic states. She is MACAN co-lead. And then in addition to her work on acidification, Katie works on marine debris, healthy ocean ecosystem indicators, sand and sediment management, Mid-Atlantic corals and canyons, and also resilience. So we'll have about 25 minutes at the end of the webinar today for any questions and comments. All participants will be muted, so during the presentation and during the question and answer session. So please ask your questions using the question or the chat box you have in your GoToWebinar control panel. And as a reminder that this webinar is being recorded and will be available on the MACAN website on the resources page with our previous webinar series. So without further ado, I'm going to hand it over to Katie to get started.
Thanks, Grace. Well, we switch over here. Can you see that all right, Grace?
Yep, looks good.
All right. Oh, let's go back. Okay, thanks, Grace. Thanks for everyone for joining us today to hear about how things are going with the development of the acidification monitoring plan in the Mid-Atlantic. So I'm going to start off and just give a, oops, I don't know why it's changing. Sorry about that, folks. Give a quick idea of why we were interested in developing a monitoring plan. The ocean, as most folks on this line know, plays a foundational role for Mid-Atlantic state economies and cultural identities. The Mid-Atlantic is embedded in the U.S. Northeast Shelf, and it's one of the most productive regions in the world, supporting diverse and abundant shellfish and finfish populations. These fisheries are a major marine resource and a critical component of the United States economy. Acidification has scientific and societal ramifications, including the alteration of ocean biogeochemistry, ecological consequences associated with altered ecosystems, and potential economic losses due to the decreased survival of commercially important organisms. A robust monitoring network plan can help in working towards an understanding of the processes associated with estuarine, coastal, and ocean acidification, and predict the potential consequences for marine resources. Furthermore, the Mid-Atlantic Regional Planning Body included the importance of understanding how acidification will impact the region in the Mid-Atlantic Regional Ocean Action Plan, which you kind of see as a screenshot on your screen, and you can find more info on, and the link at the bottom of your screen. So the implementation of a comprehensive monitoring plan can help to create a baseline and allow for the tracking of these important environmental changes over time. It will allow us to identify habitats that are susceptible to periods of low pH and or high temporal pH variability that will assist researchers and stakeholders to better understand the direct effects and ramifications ocean acidification may have to ecologically and commercially valuable species. It can provide a warning system that would assist scientists studying ecological processes, water quality managers and conservationists to monitor impacts, and commercial operators to implement adaptive strategies. It can help build and improve ecosystem models, specifically the development of coastal forecast models, with the capability to predict the variability and trajectory of the low pH water. And something we heard at the MACAN workshop in May of last year and continue to hear, and also kind of heard before that as well, is that when monitoring for acidification, it's important to measure at least 2 of the 4 carbonate chemistry parameters. Those include water partial pressure of carbon dioxide, or PCO2, potential of hydrogen, or pH, total dissolved inorganic carbon, or DIC, and total alkalinity, or TA. And I mentioned this here because this is a theme that's going to come up in kind of the rest of this presentation, really, and also for the sake of if I accidentally say PCO2 when I mean to say partial pressure of carbon dioxide, at least hopefully now there's a common understanding of what I'm trying to communicate there. So a quick primer on kind of what we understand thus far based on current monitoring and efforts in the Mid-Atlantic region. Ocean acidification, driven by the ocean's absorption of increasing atmospheric CO2, is happening on the Atlantic US shelf at rates comparable to the global average, equivalent to about a 30% increase in acidity since the Industrial Revolution. The coastal region of the Mid-Atlantic is defined by a broad continental shelf that extends out several hundred kilometers, cut by multiple shelf break canyons, and bounded offshore by the shelf break front and 5 major estuarine systems. The shelf undergoes the most extreme annual changes in temperature in the world's ocean, and these seasonal temperature changes cue a wide range of ecological processes. In late spring and early summer, a strong thermocline develops at about the 20-meter depth across the entire shelf, isolating a continuous mid-shelf cold pool of water that extends from Georges Bank to Cape Hatteras, and has been linked to the distribution and recruitment of economically valuable commercial and recreational fin and shellfish species. Upwelling occurs annually each summer. It's driven by southwest winds associated with the Bermuda High, and then Ekman forcing brings cold pool water forced to the surface layers. Off the coast of New Jersey, upwelled water that initially occurs uniformly across the coast is concentrated into an along shoreline of recurrent upwelling eddies. that are associated with the underlying topography and co-located with historical regions of high primary productivity and fishing activity and low dissolved oxygen. Through a monitoring network, we seek to better understand how these naturally occurring dynamics couple with acidifying waters. Furthermore, the coastal mid-Atlantic region is dominated by major estuaries, such as the Chesapeake Bay and Delaware estuary, as well as coastal bays like Delmarva and Barnegat Bay. Rivers and estuaries are naturally acidic due to sediments, high productivity and respiration, and lower buffering capacity due to low salinity. These systems are shallow, experience rapid temperature changes, and high biological activity that strongly influence PCO2 and pH, such as photosynthesis, benthic respiration, and root respiration in tidal marshes. Additionally, as the most densely populated and urbanized region of the United States, the developed coastal counties in the mid-Atlantic drain nutrients and other materials through the region's rivers into several major estuarine systems, causing coastal and estuarine processes that exacerbate ocean acidification. So again, we seek to better understand these interactions through a comprehensive acidification monitoring network. So as far as the makeup of the monitoring plan work group, you can see all the folks that are listed on this screen are on the work group. It's a variety of expertise with a diversity of backgrounds. And I just want to note here that these are all volunteers from the MACAN listserv. And I just want to give them a huge thank you for all of their work. We most certainly could not be developing the monitoring plan without their efforts. So thank you to them very much. And with their help, we started by developing an objective for the monitoring plan work group itself. And that is to work to develop a robust monitoring plan for the Mid-Atlantic region from estuary to open ocean in order to improve understanding of the carbonate chemistry variability and change in the region. The monitoring plan makes significant use of maps created by MACAN of historical and current monitoring locations in order to identify gaps in current monitoring efforts. At the bottom of the screen, you see 3 of the 7 maps that are all located on the Mid-Atlantic Ocean Data Portal. And I'll dive a little bit more into what we found as a result of creating these maps just in a minute. But just for reference, the 3 maps we see here on the left is kind of the base map that we created, which is all historic, current, and continuous monitoring sites that are located in the region, divided out by what type of collection for monitoring that they conduct. In the middle map is our map that just focuses on present monitoring locations, so continuous monitoring and ongoing fixed stations. And then on the right, you see a map of the different sites divided out by how many parameters they measure, so from 1 to 4 of the carbonate chemistry parameters. The monitoring plan work group then developed some logistics and organization for the group, starting with some goals as you saw, the objective, and an outline for what the monitoring plan should look like. We then decided to present it in a white paper format, and I'll go in a little bit more about what that outline and the sections of the white paper are on the next slide. We decided that the audience for the white paper would target research community to fill in the monitoring gaps, but also summarize findings to stakeholders who are interested in helping fill those gaps, as well as the Mid-Atlantic Regional Planning Body. Volunteers on the work group have self-selected themselves to lead different paper sections with monthly writing assignments and calls to discuss each of those sections and have conversations around the different topics. We routinely edit the compiled working document of the white paper, and we're hoping to have a full draft of that white paper available in the summer of this year. So as I said, the monitoring plan outline, it starts by talking about the existing monitoring, so uses those maps that I showed to talk about what currently exists and what we see as kind of overarching gaps based on, what we see in those maps. It then dives into some goals for the monitoring network, Then talks about areas of high impact, so areas that we think are really important for monitoring. It then talks about current and kind of near horizon technologies for monitoring the carbonate chemistry, and as well as water column locations, so where in the water column is important to monitor for different reasons, and also timing of monitoring, so frequency of monitoring for, again, different purposes. It then talks about optimizing the current monitoring. So the monitoring plan work group has really tried to focus on using resources efficiently. And in having that mindset, we've tried to look at what the current existing monitoring is and how we can, in more efficient and resource limited ways, improve that current monitoring for the future. It then talks about building a robust network. So what would, what are kind of the overarching gaps that would create a really robust monitoring network in the region to really understand the differences in acidification across the different ecosystems. And then talks about the importance of multi-stressor monitoring and how co-locating acidification monitoring with other parameters can help in understanding multi-stressor impacts. And finally, it dives into talking about housing the monitoring data and potential locations where this information can be digested and in one central location. So, as I said, during the development of MACAN, one of the first priorities was to develop this map that depicts past, current, and ongoing acidification monitoring in the Mid-Atlantic. And this was meant to help guide the development of the regional monitoring plan. In a concerted effort, we gathered monitoring information from the participating academic, federal, state natural resource, and commercial shellfish industry communities to develop the current interactive monitoring map that we will continue to update through MACAN efforts. You can find an archived webinar on these maps and their functionality on the MACAN website, and you can play with them at that link that's at the bottom of your screen there under the oceanography theme. But in general, by creating these maps, what did we find? So in our estuaries and bays, we found that sampling in the Mid-Atlantic estuaries and bays began as far back as 1984. And this has been a focus of sampling by state natural resource entities or through NOAA's National Estuarine Research Reserves, or NERS, network. Most estuarine sampling to date is focused on general water quality, which includes measurements of pH along with temperature, salinity, and dissolved oxygen, but not other measurements of the carbonate chemistry. Water quality measurements are collected by multiple approaches, the most common being monthly or semi-monthly sampling at set stations and tributaries in the main stem of the major estuaries. Continuous monitoring stations, such as moorings fitted with sensors, provide higher temporal resolution sampling, but have been less common in the region. A promising development is the integration of moored pH sensors at commercial shellfish hatcheries in select locations within the Chesapeake Bay, yielding partnerships between stakeholders and the academic community. Although estuarine research cruises measuring chemistry are limited and even fewer are focused on acidification sampling, they have shown the capacity for high spatial resolution in the region's estuaries, specifically in the Chesapeake and Delaware Bays. In terms of the continental shelf waters, with the exception of nearshore sampling by New Jersey Department of Environmental Protection and 3 Ocean Observing Initiative moorings conducting continuous monitoring of pH and PCO2 on the Mid-Atlantic shelf, the majority of acidification sampling in shelf waters of the Mid-Atlantic is conducted via cruises. This provides sporadic high spatial resolution sampling about every 4 years on average, which severely limits temporal resolution needed to understand daily, seasonal, and interannual variability. Sampling for water chemistry parameters in the surface waters of the United States Northeast Shelf has been conducted since 1973, with occasional measurements of carbonate chemistry. For example, the 1993 through 1996 DOE Ocean Margins Program, the 2007 and 2012 NOAA GOMET cruises, and recent NOAA Ocean Acidification Program ECOA cruises. or East Coast Ocean acidification cruises. One recent NOAA OEP-funded ECOA cruise was dedicated to acidification measurements, and another is scheduled for later this spring. These surveys depict large natural, spatial, and seasonal variability and possible decadal changes of surface carbonate chemistry on the U.S. Northeast Shelf. The underlying mechanisms causing this variability are unresolved, but likely include upwelling of the cold pool water, freshwater input from the Labrador current, and the large estuaries, air-water gas exchange, and biological processes. So in general, when we pulled together these maps, we found three overarching gaps in the monitoring. Excuse me. With the so first one being low sampling frequency. With the exception of a few fixed autonomous stations, the sampling frequency throughout much of the region is too low to adequately capture short-term episodic events that could have immediate impacts to industries and managers. For instance, the acidification-focused shelf cruises that have occurred in the Mid-Atlantic regionally, as I said, occur only every 4 years, roughly. The second overarching gap is the need to optimize one parameter sites. So even in cases where high frequency observations are being recorded, often only one acidification parameter, most commonly pH, is measured, which doesn't allow, as I've said, the full characterization of acidification. Particularly, we aren't able to understand the saturation states that can directly impact calcifying organisms. And finally, there's a need for high-resolution depth profiling sensors. Most current sampling is done at the water's surface, but subsurface waters are typically more acidic due to the biological process of remineralizing sinking particulate organic surface material. For instance, the NOAA OAP ECOA cruise in summer of 2015 revealed that the existence of low pH water in bottom cold pool waters in the Mid-Atlantic Bight Shelf. While surface water mapping of pH can be valuable, episodes of low surface pH are typically driven by mixing events where low pH water either upwells to the surface from below the thermocline or flows onto the shelf via rivers and bays. Being able to monitor pH throughout the water column is critical in order to track the movement of low pH water, understanding the variability of pH, and predict how mixing events and circulation will impact pH across the shelf. While ships can provide detailed water column profile data, their costly operation limits both temporal and spatial coverage. Moorings can collect high-resolution temporal data, but cannot resolve the spatial variability. Therefore, there's a critical need to deploy new, cost-effective technologies that can routinely provide high-resolution data on regional scales in our coastal ocean. So as I said, the work group developed goals, specifically two, to guide the development of a monitoring network in the region. The first goal is that the monitoring network should compare the gradient of estuarine to coastal to ocean acidification. So due to the diverse causes of acidification in this region and their localized implications, it is important that a monitoring network in this region depict how acidification conditions can vary across the estuarine, coastal, and ocean waters in a way that can tell a story about how acidification is impacting the various ecosystems. And second, the monitoring network should provide sufficient measuring of areas considered to be of high impact. That includes areas with commercially relevant species, areas of ecological relevance, areas of high local drivers, and areas with potential for research of possible mitigation techniques. In order to answer research questions about acidification's impacts in the Mid-Atlantic region, we'll need a monitoring network that helps us understand the spatial and temporal variability of carbonate chemistry parameters in these key locations. There are a variety of research gaps in the Mid-Atlantic that are critical in determining how the region will be impacted by and can manage for acidification conditions. The monitoring network should be developed to strategically provide data to answer research questions around some of the locations where the local ecology has a high chance of being impacted by acidification. So, as I said, there's a recognized need to monitor acidification along with other environmental stressors, as they frequently occur together and studies show may exacerbate organism response. Any one stressor, such as increasing temperature or acidification, may not itself be an issue for an organism, but as these organisms can acclimate to stress, they have ways to do that. But when more than one stressor occurs simultaneously, the organism may become overwhelmed and may not be able to deal with the changes, creating a negative response. We need to monitor acidification and study organismal response to better understand potential acclimation and adaptation strategies to both variability and long-term change in acidification. Thus, sites with existing water quality measurements that monitor stressors beyond acidification create an important opportunity for optimizing existing monitoring sites in the region. There are a variety of current technologies for monitoring the various carbonate chemistry parameters and others that have future promise. We can summarize the needs regarding the technology, though, into three categories. There's a need for better high-resolution sensors on depth profiling equipment, as pH sensors alone do not produce reliable data for complete characterization of coastal and ocean acidification. High-resolute monitoring allows better understanding of how to fully measure acidification and provide opportunities for resource management practitioners to manage coastal and ocean habitat and allow commercial shellfish operations to develop best practices to reduce impacts to future harvests. Though there is a need for autonomous in situ measurements, accurate and precise sensors for long-term deployment is just as critical. Self-calibrating systems are rare and at times require field measurements to calibrate instruments. Sensor accuracy is not only essential, but dependent on quality control technique, and that varies by user. Recommendations to reduce data skepticism would be to apply additional biogeochemical sensors that can independently validate and reveal drift. And finally, biofouling has caused issues in the accuracy of instruments and long-term immersion. There's a need for anti-fouling technologies and/or methods that create sensors capable of large-scale and long-term applications. In the Mid-Atlantic region, sample frequency has ranged from ongoing fixed stations to one-time glimpse data for chemical and/or biological conditions of a specific geographic area. For fixed stations, one to multiple parameters have been captured over 24 hours to days, and in some instances, months. In the example in this slide, we see the site highlighted on the acidification monitoring map with the little red pin there, monitors PCO2 and pH continuously since December of 2014. The Mid-Atlantic Bight is a dynamic region in which acidity can be highly variable due to pollution, currents, and biological activities, and must be taken into account when developing a monitoring plan. At minimum, annual sampling can provide some insight of long-term fluctuations, though seasonal sampling can offer further understanding of acidic conditions with seasonal variations. Monthly and at times daily measurements can capture temperature, primary production, and respiration influences on acidification. And few current monitoring efforts combine frequent monitoring with adequate parameters for acidification. For instance, there are several 24-hour continuous monitoring sites, particularly in the Chesapeake Bay, but they only observe pH in terms of the carbonate chemistry. So the monitoring frequency can be optimized for scale and data management. In terms of water column sampling, locations to monitor ocean acidification can vary based on the purpose. While many studies focus on shallow water habitats, some researchers target depths in specific zones. Monitoring takes place at certain depths depending on if the goal is to monitor impacts from anoxic conditions, mitigation techniques tested in seagrass beds, tidal-dependent shallow water sites, etc. Paired shelf and nearshore observations are needed to observe upwelling events and develop predictive models. For MACAN, the scale of this monitoring effort may depend on a variety of they may demand a variety of depths to account for the buffering gradient of estuarine to deep ocean waters. Habitats range from seagrass beds that are below 3 meters to cold water corals, which are all the way up to 6,000 meters, although commonly occur for monitoring purposes between 3 and 800. In shallow water estuaries, NIRS consistently collects data a half a meter off the bottom. And in the Chesapeake Bay, pH has been monitored at every 2 meters to the seafloor over the past 30 years. Per vessel monitoring surveys, acidification was considered the greatest at mid-level in the Chesapeake Bay, and similarly, subsurface pH was determined to be at a minimum in the summer months due to the oxidation of reduced chemicals at a depth of 11 to 13 meters, which was considered the low oxygen zone. So that's kind of an important zone to consider as we build out the monitoring plan. Okay, so some general concepts that we found in terms of gaps in the monitoring network that currently exists. Again, I'll reiterate that like other regions in the US, we're limited by resources that are available. So because of that, there are a variety of trade-offs that the monitoring plan workgroup has considered in developing a monitoring plan that achieves the goals of the network while also being efficient. In considering these trade-offs, the regional monitoring plan emphasizes optimizing the existing monitoring and structures over creating new monitoring sites. In this optimization, continuous monitoring sites are prioritized over sites with intermittent sampling for the purpose of improved temporal resolution. While the combination of monitoring PCO2 and pH are not the most effective for understanding the full impacts of acidification, they are the easiest to monitor with the best sensors currently available for in situ measurements. Though we have also recognized that ideally for aragonite saturation, it's important to measure DIC or TA with pH or PCO2 when possible, such as on cruises. We have also considered the need to monitor different habitats across different salinity gradients to understand the spectrum of impacts to the region. It may be possible to determine a relationship between salinity and total alkalinity in the Chesapeake Bay and the shelf of New Jersey. And it'll be important that monitoring is conducted that can help to establish these relationships if possible, as well as data that can be included in predictive models. To this end, a future goal under the monitoring plan for the Mid-Atlantic could be to coordinate an inter-laboratory calibration across labs in the Mid-Atlantic that accept samples for measuring carbonate chemistry parameters. Some general prioritized areas for monitoring in the Mid-Atlantic. The monitoring network should prioritize areas that are prone to acidification, where we can learn more about the drivers and include data into models. So that would be more northern latitudes of the region, which have a lower aragonite saturation naturally. And currently, the Pioneer Array southeast of Long Island monitors waters in this lower aragonite area at the surface and at depth. However, aragonite in coastal New Jersey is critical for fisheries, but it is currently only monitored on cruises like the GOMAC and the ECOA that I mentioned earlier. There's also a general lack of benthic and at-depth monitoring in the region. The benthic environment is an important habitat for benthic calcifiers and other important bottom dwellers, and this lack of benthic monitoring is true in the bays and estuaries as well as on the shelf. One area which is a likely area of impact in the benthic environment is the shelf cold pool, particularly off the coast of New Jersey, where aragonite saturation state again is naturally low, lower than at the surface. At current, monitoring in the Mid-Atlantic shelf and coastal waters in general is limited. Increasing monitoring in this area is important for understanding impacts to high populations of commercially important species. And using seasonal pH glider trips across the shelf could help to understand the cold pool on the shelf and could be equipped to take samples at surface and depth. Canyons are potential areas of high impact, particularly with the potential susceptibility of the cold water corals, which directly or indirectly support fish, marine mammal, and seabird populations. And currently, no cold water coral sites in the Mid-Atlantic canyons are monitored regularly for the carbonate chemistry parameters. Though the upcoming ECOA 2 cruise scheduled for this spring does plan to measure in known and expected cold water coral habitats. So some specific sites to create or optimize within the region. The shellfish hatcheries and nurseries in the region will be important for monitoring the impacts to this kind of critical and growing commercial industry, as they provide feedstock for the shellfish growers and have historically been a bottleneck in the industry even under historic conditions. Monitoring upstream and downstream of the hatcheries will help to understand both upstream drivers such as freshwater rain events or snow melts, and downstream drivers like ocean acidification and upwelling. There are 27 shellfish hatcheries and nurseries in the Mid-Atlantic region, 5 of which are currently monitored by a public-private partnership with industry and universities in Virginia. Upwelling in southern New Jersey around the entrance to the Delaware Bay is another important area to monitor in order to understand the local drivers of acidification, again, such as this cold pool and upwelling events. Currently, pH measurements taken at the Aquaculture Innovation Center at Rutgers University show that upwelling events are associated with a drop in pH, yet it is unknown how much upwelling occurs, for how long, and how frequently. While the upwelling may have a sporadic and limited effect on the carbonate chemistry, the cold pool on the shelf may have a stronger, more consistent effect. Since this is not monitored sufficiently, we just don't know. There are a few prime opportunities to answer questions regarding the effects of the cold pool and upwelling signals. There's an existing buoy that is about 20 kilometers offshore where additional sensors, such as a PMEL CO2 sensor system and bottom moored pH sensors, could be included to capture these signals. Monitoring in Little Egg Inlet off of Long Beach Island, New Jersey is also a prime location for understanding this signal, while also taking advantage of existing optical cables and structures left from previous monitoring. The site also provides the opportunity to compare present day with historical data from when the site was previously in operation to understand how acidification may have changed over time. Monitoring at this site would also help to tease apart effects of physiological signals in the estuary versus ocean. Furthermore, adding sensors to CBIBS buoys to measure more than pH will be another efficient way to optimize existing monitoring. In addition to being able to take advantage of existing infrastructure and entities already operating at these buoys, another benefit of these sites is that they currently monitor several other water quality parameters, creating the ability to help us understand the impacts of multi-stressors. One buoy in the CBIB system to prioritize is at Goose's Reef at the mouth of Little Choptank River, which currently includes a CFOX that is operated by the University of Delaware. The CFOX measures pH, and adding a sensor for PCO2 would optimize this site. Similarly, VIMS deployed a CFOX sensor on the York River Spit buoy in November of 2016. That could be robust if it were to include a PCO2 sensor as well. Optimizing monitoring taking place at the NIRS and NEPs monitoring sites, many of which already monitor pH and would only require an additional sensor for PCO2, could result in filling gaps in monitoring while, again, also taking advantage of existing infrastructure and folks working at those locations. And finally, I wanted to talk a little bit about some sites that currently exist, but we want to highlight as locations to maintain resources for into the future. So there are several of these sites, but first, monitoring in Harris Creek in the Chesapeake Bay at the site of an oyster sanctuary and restoration project is important to understand impacts of acidification on oyster bed restorations. Further, also the public-private partnership monitoring that I've mentioned a couple times that's taking place at the 5 commercial hatcheries in the Chesapeake Bay is also important to continue to understand how acidification may be impacting these hatcheries. Seagrass bed restoration is happening between mainland and Barrier Island off the seaside of Virginia's eastern shore. At these locations, they have reintroduced the bay scallop and the eelgrass has been restored. Monitoring happening at these locations can help glean insight into the impacts of eelgrass restoration on the carbonate chemistry, as well as impacts of acidification on the eelgrass and species using it as habitat. CBIB sites that currently monitor at least pH, dissolved oxygen, and temperature are a priority for maintaining. Particularly, there is a CBIBS buoy anticipated to be deployed this month, actually, that will have PCO2 and pH sensors at the mouth of the Chesapeake Bay that will be important for understanding the estuarine and ocean influxes and signals. Furthermore, the subset of monitoring at Chesapeake Bay sites that sample for total alkalinity and DIC are important to maintain. Thus far, samples were taken 4 times in 2016, 7 times in 2017, and are planned for 6 times in 2018. The continuous monitoring at the Pioneer Array is the only continuous offshore monitoring in the region and is thus a priority maintained. Associated Pioneer Array cruises are occurring in April of 2018, April of 2019, and August of 2019, and continued cruises beyond this timeframe will be helpful. Given the accuracy of comparing cruise ship data over the less accurate continuous sensors, continuing cruises such as the ECOA will be important for determining long-term trends off the coast and in the open ocean. So that summarizes a heck of a lot of discussion and work that's been done on the by the Monitoring Plan Work Group. I hope this was informative, if albeit a little bit long for you all on the line. And I'd love to hear your questions and your feedback on what we've done so far. I'll admit briefly that, as you saw, there's a whole bunch of other folks who are working on this with me, so I'll try to answer your questions, and if I need to go back and talk to other work group members and answer your questions in the future, I'll do that via email. But anyway, thanks again for being on the line, and I'll turn it over to Grace to see what questions have come in.
Hello. I actually don't see any questions, so I'm hoping that if there are any, maybe they just weren't updated in my screen. So Katie, I'm gonna actually ask you to check to see if you see any. I know I had that problem once before.
I do. So we have a question from Libby. How do you feel about the ability of gliders to measure OA parameters? And actually, Grace, since you're the expert there, do you mind if I turn it to you?
Yeah, no problem. I'm just still trying to figure out why I can't see the questions. Okay, well, I'll answer Libby's question. I'm feeling okay about it. I have a project funded by National Science Foundation, the OTEC program, the Ocean Technology program. We integrated a deep ISFET pH sensor into a glider payload bay. We've tested it in the lab. It seems to be pretty precise. We're comparing it with spec pH measurements. We're working with Wei-Jun Tsai's group at University of Delaware. They have a second unit that they're using for tests to look at things like response time to temperature and salinity. So we're working together on making the sensor acidification. The first deployment should be we're hoping in the next few weeks. We're still conducting tank tests at Rutgers University, along with University of Delaware. And so this sensor that we've integrated in collaboration with Seabird Scientific and with Teledyne Web it's a modified version of the depth profiling sensor they've been using on the depth profiling moorings with Ken Johnson's group. So we're feeling pretty good about it. The tests in the tank seem to be working well. So now it's just a matter of I think our main concern is seeing stratified conditions on the shelf, and with the profiling going from 20 degrees to 8 degrees within a few meters, and how will that affect pH response time. So we'll be testing all that out on the shelf in the coming months. We have 2 deployments scheduled for March, and then 1 in May, and then we have a 60-day deployment that will go from, the 2 deployments in hopefully this month, and then May will be just cross-shelf transects off the coast of New Jersey. And then we'll be collaborating with Joe Salisbury and Wei Jun Tsai's groups to deploy the glider from the East Coast Acidification cruise in July. We'll deploy the glider near Georges Bank, and it'll run a transect down to Ocean City, New Jersey. So that'll be a long deployment. And then we have a fall deployment planned as well. So we'll have seasonal, we'll be able to look at seasonal cycles, at least seasonal variability of pH, in addition to the long northeast shelf transect in the summertime. So it's left to be seen. But we're feeling confident about it right now.
All right. Thanks, Grace, for fielding that. Can you see the questions yet?
Yes, they are finally popping up. Thank you.
Good.
The next question is from Kate Morrison. Are there any lessons from other regions about ways to leverage existing funding and ways to collaborate on future proposals?
Well, so yes, I think that there's a lot that we can glean from other regions in terms of, monitoring programs. I can mention just a couple that come off the top of my head. So, work that the West Coast is doing to create a little bit more of a regional understanding of impacts to shellfish hatcheries is something that I think we've been keeping an eye on, and I kind of touched on in my presentation. It's an interesting way to kind of keep an eye on the estuaries as well as the impacts of ecologically important species. To your question about collaboration, though, I think that, to my knowledge, and certainly, Grace, you might know better, or Libby even might know better, but the collaboration across regions has been a little bit less than within regions. So that could be something that MACAN considers, and, particularly as we continue to work with our partners in the North and NECAN and in the South and SOCAN, and start to think about the particularly, I guess, North, and really focus on the Mid-Atlantic Bight, although I guess that goes down into SOCAN as well. But at any rate, I think there's potential there, but it hasn't really been seen as far as, to my knowledge.
Yeah, and this is Grace. I'll just add that, putting my Maracus hat on, we can leverage observation systems that we use through Maracus for some pH monitoring. For instance, we get certain amount of glider deployments per year in the Mid-Atlantic region through Maracus and IU's funding. So we can use, maybe one of those deployments to deploy the pH glider for that time frame. So we can leverage those types of projects to do some pH monitoring on the shelf, at least. And I know there's the CBIBs. There's a lot of people working on the CBIBs projects that I know leverage off of each other and each other's projects, and they leverage CBIBs for other projects as well. So there is some collaboration.
Yeah, that's a good point, Grace. And it also makes me think of, there's a lot of interest within members of the MACAN network to couple some of the monitoring that they're doing this spring/summer with the ECOA cruise. So, there's definitely a lot of opportunities to leverage existing funding of programs that people are doing, so that you can understand a little bit more about, coupling monitoring that happens at a NEARS, for example, with an ECOA cruise. So there are definitely things that we can glean from others, and also things that are already kind of happening internally within the Mid-Atlantic region for leveraging funding.
We have another question from Libby. I'm curious if there are any new AUV technologies for taking underway measurements in shallow estuaries. I can try to answer that. I actually don't know if there are of any. Yeah, I haven't heard of any new AUV technologies to do that. My best guess would be, or at least the best tool that might be used, best AUV tool would be like something like a Remus that can fly in shallow water. But as far as I know, there hasn't been anything integrated into a Remus. There's the wave gliders I know have integrated sensors into them for looking at acidification. But I'm not sure if any of those are, the ones that I know of have been deployed in the West Coast and maybe some in the Northeast, north of us, but I don't know any in our region at least. Katie, do you know of any?
No, I was just trying to think. Not that I'm aware of.
Okay. Ryan Ono says more of an answer to Kate's questions. The 5 hatcheries doing monitoring in Virginia actually got started with Virginia state funding after the industry requested them to get started. So the project has since evolved to find funding from other sources, for example, federal funds. So I think he just wanted to answer Kate's question. Katie, do you have any comments on his comment?
No, I think it's good.
Okay. Comment from Erica Ombres at the NOAA Ocean Acidification Program. She says, efforts like this that compile and aggregate this kind of data can lead to collaborations. All right, right. So that's good.
Yeah, right. No, well, and I think that's kind of our point, right? Is that the idea here is that by creating this regional monitor network, we are trying to create those regional efficiencies and the regional collaborations that Kate's kind of getting to. So Erica makes a good point. We're trying to help with that.
Oh, and yes, good point, Libby. Libby just brought up the point that we should mention the new Ocean Acidification Information Exchange. It's a new website. It was a site developed jointly by the NOAA Ocean Acidification Program, the Interagency Working Group on OA, and I believe NERACUS, to enable collaboration and information sharing within the OA community. So the website is oainfoexchange.org. So I'm plugging that for Libby and for us as well, as Katie and I are team leads for the Mid-Atlantic for the OA Information Exchange. So that's another way to make to build collaborations within and across regions. Let's see. The comment from Ewan Jeffrey, who just says, I might have some good information for network. So Ewan, if you can just maybe email Katie or I, or use the Mid-Atlantic email that you should see on your screen still, you can send us an email and let us know what you have in mind. And then I have a comment from Laura McKay. Actually, the Virginia Hatcheries funding started with Virginia CZM funds, Coastal Zone Management Funds. I guess it's just a clarification. I think that's it. I don't see any other questions. Does anyone else have questions? Please type in the question box. I'm not sure. I'm going to check to see if I missed any. Okay, I don't see any more. So thank you, Katie. If anybody has any more questions or comments, please send us an email at the email you see on your screen, info@midacan.org. And this, again, the recording of this webinar will be posted shortly on the website. Okay, that's it. Katie, you want to say anything else?
No, just thanks again so much. And if others have additional feedback that, comes to mind over the next few days or so, please feel free to email info@macan.org, and we'll definitely get back to you. So thanks so much again, and have a great rest of your day, everyone.
Thank you, and thank you, Katie.
You're welcome.